All right, let's step up the pace a little bit and get into some more decorative or fancier types of cuts. Let's do some beveling, some corner rounding, and then we've got a special wrench that we need to make utilizing a form cutter. Going to be machining a block of 7075 T6 aluminum. We'll be using a 1/4 inch cornering rounding end mill and then a 90-degree form tool to go ahead and put a bevel or a chamfer all the way around the part. So let's go ahead and install our parallels in the vise. Remember, we want to keep those vise jaws clean. If we're going to be using a particular setup again and again, be sure and spray a little WD-40 or spray oil against the parallel and the vise jaw so those two stick together and we don't have to constantly be cleaning the chips out from behind the parallels. Mount our block. Push down with our left hand as we secure the vise and then loosen it, making sure that everything stays tight and it doesn't shift during that tightening operation. Choose a corner rounding end mill first. It's a 4-flute design. It's going to put a very nice decorative rounded edge around our part. For doing some custom tooling, building some parts for somebody's race car, having nice round flowing edges is really important in that finished job. Alright, we can see now as we'll rotate the cutter, our actual cutting edge is right here. You can see the lower part of the cutter. So what we're going to do is rotate that around and bring that in contact with the top of our workpiece by using the quill, locking the quill down, and then we're going to lower the table 5 thousandths. And this will establish the correct cutter height. Not the depth, but the cutter height. Okay? So we'll rotate it around. We'll just come in contact, lock our quill down, go down to the knee. Drop it 5 thousandths, lock the knee in place. Now our next critical dimension is going to be the amount of cutter that we feed into the workpiece. We don't want to cut a groove along the bottom of it. We just want a full radius that we machine around that edge. So it's going to require some careful checking on our part as we feed the cutter in order to make a perfect radiused edge. We'll back the cutter away from the part, don our safety glasses. We'll turn the end mill at about 1100 RPM. So we're using aluminum, we can grab our can of WD-40. Okay, we'll conventional mill initially, and watch closely now as we bring the cutter into contact with the workpiece. Okay, we're going to look on the inside of the cutter and watch the cutter as it comes up against this vertical side. You'll see the radius starting to form at that point. Okay, and we'll just give it another 2 or 3 thou on a climb cut for a finish pass, and we're going to come back across the part. Make sure and lock your gibs down on your final pass. Nice, smooth, even rotation of the hand wheel on our y-axis. Alright, let's get our cutter out of the way. Take a look. Okay, we've machined a real nice rounded radius over the top of the part. We don't have any heavy line where we've cut it too deep. That setting is just perfect, and that really dresses up the finished part or the piece of tooling that we may be working on. Now I'm going to run the cutter around on the back side, do the same thing, and then we'll come across on these outer edges and produce a 45-degree chamfer along those, showing you two different styles of beveling the edge of our part. All right, here we go on a final pass. Now let's go ahead and switch cutters. Okay, we'll start on the front side now, providing you a little better view of what we're doing. The height adjustment, since we're cutting on a long 45-degree surface now, isn't really critical as long as we extend the point below the width of the cut. Okay, and as what we're going to do, you can see on this rounded edge, we're going to want to cut our 45-degree chamfer right down to the bottom radius, or bottom edge of the radius, where it comes into the straight section on the side of our block. Okay, and again, we're going to turn the cutter at same RPM, around 1100. Okay. Take a light pass initially. We're cutting in a climb mode right now. We're just about to full depth. Okay, we'll view the end of our part. Let's take about another 5 thousandths. Lock our table down, come back and climb cut for a final pass. It's going to produce a very decorative looking part, whether it's a tooling fixture, an instrument panel. Always take pride in the finished job. If you exhibit a little more creative talent than the machine shop down the block, I can guarantee you you're going to be busy with lots of work. If you turn out shoddy workmanship, no creative or decorative thought in mind, you're going to move on to the next guy who is a little more artistic in his machining techniques and capabilities. Okay, we're ready for final pass now. We'll pull the part out for inspection. We're using a feed rate of about 8 inches a minute. All right, let's take a look at what we've got. All right, there we have our finished block. You can see our 45-degree bevel along the side, nice and smooth, flows evenly into our 1/4-inch radius corners on the sides. So it makes a really good looking part. If we were to set that down and put a dial indicator on it, a couple of dowel pins, a hold down clamp somewhere, we'd have a real nice base for a piece of tooling that anybody can be proud of. Remember to have a little finesse in your work. We want to turn out something that looks good as well as functions for the intended task. Now let's take a look at another way to apply a bevel using a V-block. All right, if you don't have a form cutter, yet you still want to cut a nice beveled edge on the part, what do? Rather than tilt the head and go through the hassles and pains of retramming the head back in, simply insert your work in a V-block. Use a penny or something to insulate the work between your hold down clamp. Hold it in place, and we can use a conventional end mill to come in and cut a bevel all the way around that part. Bear with me while I change cutters. I'll be right with you. Again, don't be afraid to just grab some material if you see it on sale somewhere at your local metal shop or steel supply house, and they've got a load of aluminum or steel that's around there that you can buy for a bargain. Cash in 10, 15, 20 bucks worth. Take it home, practice, build yourself some tooling fixtures, get familiar with the machine, get familiar with the different cutting operations, so when it comes time to perform a job, it just becomes second nature and you can snap your fingers and the parts just pour from the machine. Okay, we've got our part set up. We're going to bring our cutter down, just come in contact with the work, lock our quill down. Going to raise the knee 10, 15 thousandths, and watch now as we again put the same type of a bevel or chamfer on our top edge of our part. Do these in series for the different widths and dimensions that you have. Remember to keep track of how many thousandths you feed the cutter into the workpiece so you can duplicate that on all the other existing edges simply by rotating the part in the V-block. Have a nice smooth feed rate as we cleave off that little chamfer across the top of the part. Okay, we've got a real nice bevel on that side. Simply reverse the part. Keep our cutter setting the same. Wipe out our V-block because we've got some chips and stuff to contend with. If you get a chip underneath it, you're not going to have a uniform chamfer around your part. Always take our hand, wipe it across the part. We can feel really well. Don't take for granted that simply one pass of the towel or shop cloth got all of the chips out of the way. Hold our part down into the V-block, tighten our clamp, and with the cutter on the same setting, we're just going to proceed to come across the top of the part, putting an absolutely identical chamfer on the opposite side. Now, let's take a minute and install a form tool, and I'll show you how to build a special wrench, or at least one that I manufacture for different companies around the country. All right, we've machined up a blank for the particular wrench again that we manufacture. This wrench is for the ever popular Remington 700. We sell these to gunsmiths and Remington owners all across the country. You can see the formed profile that we're going to be machining. The most efficient way to do that is with a form cutter. So let's go ahead and install our blank in the vise, clamp it down, and I'll show you how to properly set the height for the form cutter. Set it up on a parallel, an adequate amount exposed. We want to keep a nice rigid setup now. Tighten our vise down. This is a sample of our form cutter. We showed you this before when we made a sample cut on a piece of aluminum. We have a radius ground in here that matches the profile of the body of our wrench. Then these flats are going to come in and cut the rails, if you will, on the wrench. So we've got it installed in our AccuPro tool holder, good rigid setup. Let's install it in the mill. Remember, we talked earlier when you have form cutters done that you want to establish from the bottom of the cutter to the center of the radius. And this is done on an optical comparator for whomever is grinding your form tools for you. Then they're simply going to inscribe along the cutter what that dimension is. This particular one is 792 thousandths. So once we come in contact with the top of the part, we simply raise the bed or lower the quill 792 thousandths in order to center this radius on our workpiece. I'm going to bring the cutter over the top of the part, lower the quill until we just spot on the cutter, lower the bed 5 thousandths, move our cutter off. We're going to turn the machine on now. We're going to run this part at around 325 RPM. We're machining a piece of heat-treated steel. Shift your machine into back gear, lock the quill down. Index our part over the top. Slowly raise until we just spot on top of our part. Loosen the lock ring on the knee. Set our dial at 0 and then proceed to raise the bed half of the diameter of our part. Got a 1-inch piece of material here, so we're going to go a 1/2 inch plus 792 thousandths, okay? And that'll put us on the center of the part. Okay, we made those adjustments on the Z-axis. Okay, we're just going to come in now in a conventional milling direction. Come in contact with the work. Back away from it. We're going to apply a little bit of cutting fluid. We'll use a good sulfur-based oil. Okay, are you listening to the cutter? What you're doing is making little chirping sounds, isn't it? We're also getting a little bit of clunking out of it. What is that telling us? You're probably running the cutter a little too slow. All right, so after we make this pass, let's go back and change speeds and you let me know if it doesn't sound like a more appropriate speed for this particular cutter. Okay, we're going to shift gears. Let's try 660 RPM. See what that sounds like. Okay, we're still getting a little bit of noise. Increase our feed rate a little bit. Come across it with a climb cut. Okay, what are your thoughts? We've shown you two speeds, two feeds. Which would you prefer? All right, we've got two ways to go. We can lighten the cut up a little bit, continue at 600 RPM, taking a little bit heavier cut. The machine is talking to us again. We'll watch in a climb cutting mode if we take, again, just a little bit of a lighter cut. Not a lot to suck the cutter along. But we machine pretty smooth under those conditions, but we're still getting a lot of chatter out of the part. So probably we're better off opting for that speed of 325, slowing our feed rate down just a little bit. So you can see how to fine-tune the cutting operation based on what the machine is telling us by the chatter, by the vibration and noise. So we'll just take our time, we'll putt along here in back gear, adjust our feed rate accordingly. Remember, we've got a lot of material exposed from the vise. It's trying to spring away from the cutter. Keep plenty of fluid on the cutter as we're machining. All right, we've given you different examples of the form cutters. I'm going to go ahead and finish up on the back side. I'll join you in just a minute with the finished product for final review. Okay, you can see the profile, the radius top edge here matching the diameter of the part that we have. So that's an example of what a form cutter can do. If you've got some specialty operations that are difficult to machine in other axes, spend a few extra bucks, have some form cutters done, make the necessary tooling to hold your parts and pieces, and you'll come out with a dynamite looking job when you're done. All right, that's pretty well a wrap on rounding corners, using form tools, using a V-block to cut a bevel or a chamfer on something. Let's continue. It's now time to add a little bit of frosting to our work project. We've inserted our corner rounding end mill, 1/4 inch radius. We're going to go ahead and machine a radius profile around all 4 edges of our part. Remember the suggestions that we made earlier when we showed you how to use a corner rounding end mill. We've got our lead cutting edge here, and we're going to want to gently bring that down in contact with the work, lock the quill down, go to the knee and lower the table 5/1000ths of an inch. And then lock the knee in at that point. So we've established the correct cutting height of the cutter. Back our cutter away from the part. Now we're ready to cut our way around the block. Remember, we just want the radius to come in contact with the vertical part of the block. We don't want to have a stripe cut around it. Take your time, make sure and use the climb cut on the finished pass now. Nice, smooth, uniform feed. All right, we're on the last pass. We're rounding off all of the corners on our block. We're going to remove the block, burr it, turn it upside down, and we're going to put a 45-degree beveled cut around all four edges on the other side. If you have a form tool, this is a good time to use it. If not, grab the V-block, insert it in the V-block, and make separate passes, keeping them all uniform. Remember, there's more than one way to skin the cat. All right, since I have a form cutter, I'm going to take the easy way out and race around the block now, cutting a uniform chamfer at 45 degrees. Anytime that we're using this type of a cutter, we're going to bring the cutter into contact with the workpiece. You're going to have to get your eye down there close to the work so we can see the contact point being made. Okay, and then once we've made contact, we can either set our digital readout or lock down our bed, loosen the lock ring on our dial, set it at 0, and take a uniform amount off all the way around the block, equally on 4 sides. We want a nice continuous chamfer around all 4 sides of the part. It doesn't want to be thick on one side and thin on the other, all right? All right, before we continue, let's take a couple of minutes and review what we've done to the block already. We've dimensioned our block in thickness, length, and width. We've drilled and reamed 4 holes. We've drilled a hole in the center. We've put a 45-degree chamfer around all 4 corners of the part to a uniform thickness. On the other side of the block, we've taken our corner rounding mill and we've put 4 equally radiused edges on our part. We've dial indicated the center hole in, and we've counterbored that to a dimension of 1 inch and 50 thousandths and a depth of 700 thousandths. So if your block doesn't look like this, hit the rewind and go back to the beginning and find out where you missed it. We also have 3 holes that are equally spaced, centered in our block, drilled and tapped to a 1/4-20 with the appropriate countersinking on the top. Next, let's take a look at the digital readout. Really God's gift to the machinist world. It allows us to pay attention to the digital and not worry about constantly stopping, locking the gibs, taking the backlash out of our X and Y axis. We simply take a reference point, kind of like your GPS, off of our material, plug it into our digital readout, and we can come back to that same point for referencing. For drilling hole patterns, doing elaborate drill and tapping schemes, milling of slots, intersecting of slots, etc., the digital readout is an invaluable source on your machine. For those of you that are purchasing a used machine, many used machines now come with a digital readout. If the individual had a pretty decent working shop, he probably had a digital readout to accompany the mill. So it's an extra bonus when you're purchasing that used machine. All right, we've got a block of aluminum that we've set up in the mill vise again. The width of the block is 2 inches, 620 thousandths. The length of the block is 3 inches, 925 thousandths. We're going to insert our edge finder into the drill chuck. We're going to locate an edge and we're going to find the exact center of our block. All right, but before we do, let's assume that we went down to the mailbox and lo and behold, we received the contract from Uncle Sam to make 500,000 of these blocks, and we just jumped for joy, and we want to do it fast and economically. We're going to install what's called a production stop or a work stop on the mill vise. And that way, once we've established references for the location of our block, we can simply take one block in and out of the machine and insert the next block, provided they're the same size and we're holding tolerance, and have excellent repeatability. And this simply just clamps on to the vise jaw. Take an Allen wrench, tighten it in place, and we're going to butt one edge of it up against our workpiece. So each and every time we loosen the vise, take that block out, push it right up against the stop, we're going to get excellent repeatability. Now let's use our edge finder and come in and find the center of the block. We'll work off of the 2-inch 620 thousandths side first. We're going to take half of that, which is 1-inch 310 thousandths, plus the 100 thousandths offset from our edge finder. Remember, the edge finder is 200 thousandths in diameter. We're simply bringing it up until we contact the edge of the work. All right, we'll turn our machine on. Let's bring the edge finder up in contact with the work. Okay, and we just saw it kick off. So at that point, we're just going to back it out a little bit. Now let's go up to the digital readout. Okay, most digital readouts are going to have a keyboard associated with them. We've got 0, preset, enter, and memory. Once we've established a reference, we're just going to go up and zero out that reference. Now we're ready to establish our own reference, very similar to our GPS, finding the way back to the truck. Raise our quill, keep an eye on the digital readout. We know that our half dimension is 1-inch 310 thousandths plus the 100 thousandths for the edge finder, so we're going to move the x-axis 1-inch 410 thousandths. All right, here we go. Okay, we're sneaking up on 400 now. 399, 1-inch 400, an additional 10 thousandths. And we're done. Okay, at that point, now we can go back and establish our center 0. We'll work off of the edge now at 3 inches, 925 thousandths. Same procedure. Bring our edge finder in contact with our workpiece till we just see the offset. We're going to go back to the digital and we're going to zero the y-axis. I wish I could make the national debt go away that quick. Simply push a button. All right, so now we need to figure the distance, or the half mark, on 3 inches, 925 thousandths. Simply using the calculator, that dimension is 1 inch, 962 and a half thousandths, plus 100. So we've got 2 inches, 62 and a half thousandths to the center of the part. Watch our digital now. Okay, and the y-axis, 2 inches, $62 and a half thousandths. Now we've plotted the exact center of our workpiece. Very, very important. Now that we've plotted that, we're going to go ahead. We've got a different hole pattern to drill based upon the center of the hole. So we're simply going to use our center drill now. We're going to go through and center drill all of our holes. Then we can come back around and drill the holes from there. Again, the advantage of the digital readout lets us keep track of where we're at without constantly locking down the ways, adjusting the dials and the lock nuts. We simply use the digital readout and we're ready to go. All right, let's use this as a reference. Going to drill our first hole right in the center. We are going to index to the left on our x-axis 3/4 of an inch. So 0.750. Remember our decimal system from our earlier review. Okay, now we're going to move on the y-axis 1.5 inches. Okay, there we are. We've offset 750 thousandths on the x-axis. We've moved on the y-axis 1.5 inches. We're now ready to come down and center drill another hole. We're going to index now over on the x-axis to the right, back to center. Watch our digital readout now. Okay, we're now at 0, back at our original setting, 750 thousandths. You can just sit there and watch the numbers grow. Okay, we're ready to center drill another hole. Move down. Okay, now we're going to come in, center drill our third hole. We're going to index over to the left now for our final hole. Presto changeo. We've now located 4 holes, actually 5, from our center reference all the way around the periphery of the block. We've center drilled them. If we're going to drill and tap or put in a larger drill, we simply do so at this point, and again, we can chase those hole patterns all the way around the block. Keep in mind, as far as time is concerned, if we have a long distance between holes, we're better off from a time standpoint to simply go in, drill, ream, tap, whatever we're going to do off of that one position rather than chase the holes all the way around a rather large part. Okay, finish the operation as you go. That way when we get to the last hole, we're done. We're not continually chasing our tail. Now, if we want to go back and reference the center of our part, we're going to mill a square around the center of the part. So we'll simply watch our dials again. We're going to locate back to the center of our part. Moving the y-axis now. Now we're moving the x-axis. We're going to reinsert our center drill and come back. Watch closely now. We're in the exact center of our hole. We're now ready to remove the center drill, remove our chuck, and let's go ahead and mill a square around that part with a designated offset. Okay, we're going to offset our square 3/4 of an inch from the center of our hole. We simply move the x-axis over 750 thousandths. Okay, we can lock our table down at that reference. Start our cutter. Come in contact with our workpiece, establish a 0 on the z-axis now, so we can cut that slot to a specific depth. We're using a 2-flute center cutting end mill. We can cut that slot to a depth of 100 thousandths. Now, from that 0 setting, we're going to want to go 3/4 of an inch each direction. So very carefully advance our slot. $750, come back the other direction. $750 thou, loosen our gib. Going to move the x-axis. We're going back to 0 setting now. Okay, we're at the center of the part. 750 thousandths, the other side of it. Okay, now we're going to lock down our quill and go the other direction. Now we'll move back to our original slot. All right, let's get rid of the chips and uncover a masterpiece. All right, there we have it. We've in essence built a moat or a cooling passage around our particular part by the use of the digital readout. A whole lot easier and faster than we could by trying to keep track of the revolutions and dials, backlash, etc. So as you can see, the digital readout is really a gift. It enables us to perform our tasks much faster than we would with the hand dials. Read the booklet, get familiar with it, do a few simple layout patterns on a piece of material, and become familiar with it, and you'll find that it's the best friend you'll ever have on the milling machine. Another task we may be called upon to do in the machine shop, and that is boring a hole. We can drill and ream holes, but only to a certain size, and then boring becomes a much more practical approach for a given hole diameter. Old farmer down the street had brought in a sample part for us, and he needs this hole picked up and bored to a larger diameter. It's probably about, an inch diameter right now, and he wants to open it up to 1.25 inches. We don't have an 1.25 inch drill. It needs to be a precise fit to mate with this hole pattern that he has. I guess it bolts up on the side of his diesel motor on the tractor. It's some type of a flange adapter that he has. So in order to do this, we're going to need to come in and dial indicate the hole. But before we do that, let's take a look at a Criterion boring bar that we will be using in the boring process. This particular boring head is made by the folks at Criterion in Costa Mesa, California. Probably one of the finest boring heads that you can buy. Again, they come in different sizes. This one has an R8 stub arbor on it, so it's going to replace the contour of an R8 collet. This is a model DBL 202. The DBL stands for double hole, so you can see if we're going to be boring a larger hole, we would simply offset our cutter, and that increases the range at which we can bore. The boring tool works basically on a large dovetailed assembly. We've got a dial here that's graduated in thousandths of an inch on the diameter that we're dealing with. Okay, it's very important you keep that in mind, that this is working off of the diameter. The 3 set screws that you see on the side are simply gib block screws, if you will, very similar to what we have on the mill. We snug the outer 2, we leave those alone, and then we loosen and tighten the center one in order to make our adjustment. So we'd simply loosen that, go to our dial, and then increase or decrease the number of thousandths of inch that we want to do our hole. Now if we look on the side, you can see how the dovetail itself is becoming exposed. There's a little screw in the side that we look in the back here, and that's also a guide as to the amount of offset that we can have in this particular boring head before we need to switch to the second hole in the bottom. So we'll go ahead and advance the boring head out quickly and show you its maximum range with the center offset. Okay, when you see the screw become flush with the outside of the boring head body, that's about the maximum application. All right, stop at that point, use a larger boring tool, or simply offset to the next hole in the bottom, and this will increase our bore diameter. Now let's take a minute and talk about the boring cutter itself that goes in the boring head. This particular cutter is a carbide inserted cutter, very similar to what we would use in the lathe if we were boring as well. You can see the carbide insert on the end. It's got a 1/2 inch diameter shank that goes into our boring head. You can get these in different lengths. Again, like an end mill, like a collet, we want to keep as rigid a setup as we can. If we're only boring a 1/2 inch or an inch thick piece of material, the boring bar itself should only protrude maybe an inch, 1.25 inches. Okay, again, this gives us maximum rigidity, which is also going to provide accuracy in the bored hole. If we have a real long boring tool, it's going to have a tendency to flex on us, so we're going to want to continue when we get close to our finished diameter to continue making passes, eliminating the spring or flex out of the boring tool, and then measure for final size and make the necessary adjustments from there. All right, we'll go ahead and retract the boring head. We're going to locate the hole now. Remember the tip that we showed you earlier about taking an end mill or something in the drill chuck or collet and using it as a quick guide to get to the center of our hole, and then we can fine tune it with the dial indicator. So we're simply going to install it, eyeball that into place. Okay, that looks pretty close by eye. Let's go ahead and put the coax indicator in and see how close we got it. Okay, we're going to go ahead and preload our dial. Bring it down to about the center of our hole in terms of width. Okay, we'll shift our machine into back gear. Okay, make sure when we're using the coax indicator that we hold on to the little stem here. We can mount something on the table as a little back bar, but we don't want to allow this to be swinging around. We can damage our coax indicator. So I like to just hold on to it while I make my adjustments. Okay, we got her pretty close, within about 15 thousandths. So we're going to turn the y-axis. Come over to the x-axis now. Okay, now we're starting to fine-tune the hole. Okay, there we go. We've got that hole indicated within about 1/10. Shut the machine off, lock our gibs down. Got a positive location on that hole. We don't want anything to shift or change. And let's remove our coax indicator. For those of you that have dialed in a lot of holes the old-fashioned way, before the brains at Blake Manufacturing came up with a coax indicator, you can see what an invaluable tool this is, and a time-saving tool as well. If we've got a lot of holes to do, this is going to save us a lot of time, giving us more time to spend that money we're making. Okay, install the boring head into the spindle, apply the brake, tighten it up. We're going to go ahead and lower the quill down, and we can see that we need to offset the cutter more in order to get the diameter that we desire. Okay, lower the boring tool down, and then we're going to start advancing the cutting edge towards the edge of our hole. Okay, now we've got quite a ways to bore, so we're just going to come up and kiss or come in contact with the edge of the hole, remove our Allen wrench that we made the adjustment with, and then tighten down the center screw. Okay, so now we're at a fixed position. Let's go ahead and see what kind of contact we have and clean up that hole. Alright, so we're going to turn this at about 1115 RPM, or second gear in the direct drive. Okay, we're just a little bit under. Go ahead and loosen again and advance our tool out. Let's go another 20 thou. There we go. Now we're just starting to cut. We're manually pulling the quill down in that boring operation. Now you're going to see, because of the offset, that we've got kind of a counterbalance problem occurring here. So we don't want to really turn it up fast and accentuate that counterbalance. Around 1100 RPM, depending upon the diameter of holes that we're boring, is about right. Now remember earlier when we were going over describing different parts of the mill, we have a power feed application on our milling machine. Let's go ahead and put that into use and save the wear and tear on the right arm of pulling that quill down. We're going to take another 20 thousandths pass. I like bringing the cutter down in contact of the work, retracting it 30-40 thousandths before we start the machine up. Now let's move to the top of the mill head and make the necessary adjustments to engage the power feed. Alright, this is our power drive on the spindle. We need to engage that gear. Okay, you'll have a little sign usually above them that says in and out. We want to engage that gear. We're now ready to turn the machine on. Do not make this adjustment while the machine is running. Always turn the machine off before engaging that gear. Go ahead and turn the machine on. We're going to come over and establish our drive direction by retracting or pushing in our gear here. We've got our feed set at 3 thousandths per revolution. Now let's engage our clutch and go ahead and bore through that hole on power feed. Once you clear, simply disengage the clutch, manually retract it. We're ready to make another adjustment on the boring head, again increasing the diameter of the hole. Depending upon the material that you're doing, we can take a pretty heavy cut. Let's go ahead and make this next cut a little bit heavier, about 80 thousandths. Okay, you can see we're removing quite a bit more material at that point. Now, when we get close to our finished diameter, you can see we've made a pass. We've got quite a bit of protrusion of the boring bar itself in the boring head, so we're getting a little bit of flex. So let's go ahead and retract the head, engage the power feed again, and watch it take off those microscopic shavings from the flexation that we had. Okay? Once we've got that to final size, we can go ahead and shut the machine off. Retract our cutter. Now we can take an accurate measurement of our hole to determine how many more thousandths that we want to take. We can also vary the rotation or the amount of feed that we have in the power feed. 3 thousandths is usually about right when we're dealing with aluminum. Each application is going to vary though. If we're machining hardened steel, go to the 1.5 thousandths per revolution feed. If we're going through some plastic or material that we can really pour the coal to it, go ahead and make your adjustment up to 6 thousandths. All right, let's take a measurement of the hole, see where we're at. Go ahead and use our dial calipers for this. Okay, we're at 1 inch, 229 to 30 thousandths in hole diameter. So we're going to go ahead and sneak up on it. Let's take another 15 at a pass, and that'll take us around 245, and we can make our final adjustments from there. Let's give you a close-up view of our adjustment now. You can see the little dial on the inside of the boring head. Simply insert our Allen wrench. There's 5 thousandths, 10 thousandths, 15 thousandths. We're going to go ahead and lock it down. You're boring a real precise hole. I'll go through it 2 or 3 times to where I don't have any cutting action taking place. Allowing the cutter to spring back into a natural or relaxed mode, if you will. We're just shaving off 10 thousandths of an inch at that time. Okay, let's stop the machine, make sure our hole is clean, take another measurement. Okay, we've got around 246 thousandths. Let's take another 4, and that should pretty well bring our part into specification for the farmer down the road. Give it a little shot of WD-40. Okay, let's check our hole and see if it's the final dimension. Okay, there we go, 1 inch 250, right on the money. Now, let's go up and work to the top of the mill again and practice the auto disengage mode, if you will, working against the quill stop. We can take our tool, we know what depth that we want to bore to or just through the hole. We're going to go ahead and bring our quill stop in, lock it in place with the lock ring, retract our tool. Let's go ahead and bore down and watch it disengage at that point. This is really handy if we need to bore to a specific depth. Okay, as soon as we come down and bottom, automatically disengage. Okay, we can retract our tool. For boring a relief in something or counter boring a specific hole, this is a really good method to use in order to do it accurately. As that quill comes down, bottom's there, it's going to disengage our feed, and we can retract the tool and we're ready to go. Now let's take a look at another type of boring using an end mill. We've showed you secrets of drilling, reaming, and tapping and boring. Now let's see what an end mill can do if we don't have a drill of a specific size or the hole diameter. It's not really critical. Watch closely. Go ahead and remove Farmer John's part. We've got a piece of extruded aluminum that we need to bore a couple of holes in. We'll set it up on our parallels. Clamp it tight, remove the parallels. We don't want to run our end mill down into the top of the parallels because the parallel usually wins and the cutter loses at that stage of the game. Okay, let's go ahead and install our drill chuck because we can rough the hole out by using a drill. For those of you that didn't fall asleep during the boring operation that we just performed, anytime we drill a hole, we need to do what? You guessed it, use a center drill. Okay, so we're going to go ahead and install our center drill, push it up against the top plate, retract it 30-40 thousandths, and we'll go ahead and locate our hole. You can see how fast the Albrecht chuck is. If we had to look around for the chuck key, by the time we had that done, we could have changed 3 or 4 drills in the Albrecht. Okay, you see we've got a long stringy chip. Take your time and uncoil it by hand. Be really careful, don't jerk it. And by all means, don't get your hand next to it if the drill is running. Alright, so we've roughed out our hole to 15-30 seconds. Now let's go ahead and use an end mill to enlarge the hole to 3/4 of an inch. In order to get an accurate hole when we are boring with an end mill, we need to turn it in back gear a little bit slower than we normally would for a milling or facing operation. Use plenty of fluid and make sure that we raise the knee on the Z-axis in order to let the cutter remove material. For an accurate hole, we don't want to be feeding the mill cutter down with the quill. We'll set up some chatter if we try and do that, simply because of the surface area. So we've got it running in back gear. If we're careful and we want to apply a little bit of tension to the gib on the quill, we can do that, but I prefer to use the knee. Go ahead and bring our cutter down, contact our workpiece, back it off 5 or 10 thousandths by lowering the knee. Okay, and we're going to turn it in back gear at around 325, 200, well, let's go 210 RPM. That sounds like a pretty good number. Engage the necessary levers in order to switch the machine into back gear. Put on your safety glasses, grab your oil bottle, and we're ready to flip the switch. And apply a little amount of oil, and then we're just going to start raising the bed, clearing the chips as we go. When we clear a chip, we just simply back off and allow the chip to break free from the flutes of the cutters. Go 50, 60 thousandths at a time, depending upon the chip load that we're pulling. All right, we've bored a very accurate 3/4 inch diameter hole using an end mill. Now let's try the same thing by the use of the quill. See if we can develop a little bit of chatter showing you what that looks like. Okay, we've got a nice polished hole. Everything works out really good. Let's take a measurement while we're at it and see just how accurate that hole is. I think we've got a undersized end mill there a little bit. I must have had that in the shop for regrind. But we get 738 thousandths. Now let's clean the mill cutter off and take a measurement across the two cutting flutes. And I get 737. So as best we can measure using the dial calipers, we've only increased the diameter of that hole approximately 1/1000 of an inch, which is more than adequate for most boring operations that we would be doing of this nature. Okay, now let's go ahead and repeat the process and try feeding that cutter down in back gear by using the quill and see what happens. So just give you a little more practice for changing collets, center drilling and drilling. Okay, let's index our hole. In order to get a really round hole, by round we're talking really precise now, just not a round hole that a bolt goes through, you really need to drill, ream, or drill, ream, bore in that order. Okay, if you've got to have a very precise hole, reaming is probably your best bet. If we're dealing with large diameter holes, obviously we can't buy a 6-inch diameter reamer, then boring or lapping come into play. Okay, what happened there? For all of you that was listening and paying attention, we heard a tremendous amount of chatter take place when we brought the drill in contact with our work. You guessed it. We had the RPM just a little too fast. Okay, we're running that drill at around 1750, taking a pretty heavy cut. Let's slow it down to 1100 where it really belongs and try it again. Remove our chips. Now listen closely. See how much smoother that sounds? Again, that was an application where the machine was talking at us. Hey, hey, hold it. You're going a little too fast. Slow her down. All right, now let's insert the end mill. And continue with this boring process. Okay, again, we're going to run the same RPM in back gear at 210. So we're going to make an adjustment in the pulleys. Shift gears from direct drive to back gear. Okay, we're going to go ahead and bring the cutter down against the workpiece. Back off about 5 thousandths. We're just going to apply a tiny bit of drag on the quill. Apply some oil and let's see what happens. Okay, we can use that very successfully. A little bit of drag applied. Using the end mill to bore a slightly larger hole in a plunge cut fashion. Okay, we're not getting much chatter, that's just the whine out of the gear. If we were to turn it at any faster RPM though, during a hand feed from the quill, we're probably going to pick up a little bit of chatter. All right? So that pretty well concludes our session on boring. I hope that you've learned some things and that you've already got that catalog out purchasing the Criterion boring head. We've shown you different applications. We've shown you how to use the power feed. I think you're pretty well prepared to grab a piece of stock and get with the program. All right, our next step in our practice block involves turning the block upside down. We're going to put our 4 dowel pinned holes on the bottom. We're going to dial indicate the center hole, and then we're going to counterbore that with our Criterion boring head to a diameter of 1 inch and 50 thousandths and a depth of 700 thousandths. I'm going to be using the coax indicator. If you don't have a coax indicator, grab your dial indicator and get with it. All right, I'm done. How about you? Before we get started with the boring operation, I'm going to show you a little tip on how to carefully gauge the depth of our hole. We're going to bring our boring head down in contact with our workpiece. Lock the quill in place, and again we're going to use our quill stop. We'll be boring this hole with a power feed, or you can do it manually, whatever you're most comfortable with. But we're going to bring our quill stop up, insert our gauge block at 700 thousandths, lock it into place. This way, either manually or with the power feed, we know when we've achieved the right depth. Another tip is to make a gauge block out of a small adjustable parallel. Simply adjust it to whatever depth we want, lock down our lock screw, and now this becomes our master or our gauge block to insert between our quill stop. Bring our lock ring up, lock them in place, remove that, and we're located within just a few thousandths of the proper depth. Okay, we're going to go ahead and feed this manually. And then we'll switch over later on and do it with the power feed so you get a feel for both. Or cut our little shot of WD-40. You can take around 50 to 60 thousandths per pass, roughing out the hole. Now for those of you that think you're a little bit smarter than the average bear, I don't want you cheating and running a 1-inch end mill down the hole first. The significance of this is learning to use the boring head. Stop and clear those chips away. Don't let them build up on you. Okay, let's take a check and see how close we're getting. We're at around 925 right now. Remember, our hole diameter is 1 inch and 50 thousandths. Okay, now we're going to go ahead and engage the power feed. We'll try a couple of passes on the power feed. We're at 965, so we're starting to get pretty close. Okay, we'll take a minute, we'll grab the air hose and clean out our hole. Try and get a pretty accurate dimension here. Remember to be very gentle on the air hose. We don't want to blow chips clear across the shop. We don't want to blow them into somebody that's standing across the room admiring our handiwork. Okay, we've got a hole diameter of 1 inch and 26 thousandths. We've got 24 to go. We'll go ahead and sneak up on that. We'll take it in a couple of passes. Remember, we've got a little bit of flex in the cutter, so we want to keep that in mind as we make our adjustment. right, let's go in for another check. Blow our hole out. If you've got a telescoping gauge or another precise method for measuring the holes outside of the dial calipers, by all means use them. Okay, we're 1 inch and 42 thousandths. So we've got 8 thousandths to go. I'm going to go ahead and take 7 thousandths off in this next pass and allow for a thousandth of spring back in the cutter. Let's see how close we get. We're using a feed rate of 1.5 thousandths per revolution. We're entering now what we think is going to be our final pass. Retract our cutter and start it down one more time in case we've got any spring back in the boring tool. Looks like we're taking just a couple of tenths off in this last pass. All right, let's take our final measurement now. I'm going to go ahead and lower the bed a little bit. Anytime you make any changes, make sure and lock the dial down so we can repeat our depth as we get a more accurate measurement. Okay, we're going to lower the bed 400 thousandths so we can get our dial calipers in the hole. Rotate our boring tool out of the way there. Okay, we're right on 101 inch and 50 thousandths, give or take a few tenths. So that's close enough for our work block. I don't want to see any blocks showing up for inspection that are 1 inch 55 thousandths, 1 inch 60 thousandths, okay? We're going to give you a little bit of leeway there, a couple of tenths. No, we'll allow 1.5 thou on that diameter. So pay attention, use a good sharp cutter. Remember to take into effect the spring back in the boring tool.
Attention, gun owners, collectors, hobby gunsmiths, FFL dealers, and professional gunsmiths. The American Gunsmithing Institute offers you comprehensive training and information through our exclusive instructional videos. AGI's complete line of how-to gunsmithing kits will give you the results you're looking for, whether you're refinishing a stock or glass bedding a rifle. Each kit comes complete with AGI-approved products and a video instruction manual featuring a master gunsmith. Whether the process is as simple as tactical spray coating or as involved as parkerizing, we guide you step by step as only AGI can, giving you the tips and techniques you need to avoid mistakes and get professional results. In the AGI Armorers series, each course covers a specific firearm. We give a brief overview of the history, demonstrate the design and function using cutaways, and guide you step by step through complete disassembly and reassembly down to the last part. We also show proper cleaning and lubrication methods, troubleshooting tips, repair techniques, and review available accessories. No other video will give you this level of instruction on one specific firearm. We offer courses on all the popular makes and models. Want to learn more about general gunsmithing techniques? In AGI's complete practical gunsmithing course, we show you how to set up your shop, and then we cover step by step the most common gunsmithing projects. In over 4 hours of exclusive video, a master gunsmith will teach you precision scope mounting, sight installation, stock repair, cold bluing, glass bedding, recoil pad installation, how to remove a dent from a shotgun barrel, and many other tricks of the trade. If you're interested in becoming a gunsmith, the American Gunsmithing Institute is internationally recognized for our professional gunsmithing course. It contains over 100 hours of detailed instruction on 56 videotapes. Instructor Robert H. Dunlap has over 30 years of professional gunsmithing experience and has taught professionally for 20 years at one of the nation's top gunsmithing schools. He will guide you step by step through the design, troubleshooting, and repair of all types of pistols, revolvers, shotguns, rifles, and .22s. Our close-up video techniques, combined with Mr. Dunlap's exclusive knowledge and unique teaching methods, provide you the opportunity to become an AGI-tested, certified gunsmith. Whatever your gunsmithing needs, AGI can provide you with the knowledge and materials you need to successfully customize, repair, and refinish your firearms. For a complete catalog featuring all of the AGI products, simply contact the American Gunsmithing Institute at 1325 Imola Avenue West, number 504, Napa, California 94559, or call 1-800-797-0867. Or you can browse through our color catalog with images from the actual videos at our website. Get online with the American Gunsmithing Institute at http://www.americangunsmith.com.